Okay. Hello. I think we had a good discussion in the breakout session on cardiovascular diseases. And I just would like to start off with this slide, that there's really an unmet need in the treatment of cardiovascular diseases. It's just to remind you, it's an important disease, which holds true, I guess, for many of the aspects we have discussed today. But it's really important to stress this because the objectives here are actually for a variety of cardiac conditions to actually prevent cardiomyocyte cell death, to enhance cardiac regeneration if this is possible, and activate self-repair. And single-cell sequencing can really contribute not only to lay the basic groundwork here, but also to monitor progress in certain therapies and during diverse states of cardiovascular diseases. This is just a reminder that we can use cells as a therapeutic target to stimulate them for regenerative processes in the heart. And I think we need to ultimately monitor this not only at baseline, but also after therapeutic intervention, whether this is successful on the single cell level, and so that has this additional side to this. But let me come to our discussions, and I think it's important to say that the heart is a bit, or perhaps a bit more difficult than other organs in certain aspects that I will come to, but many of these aspects have been just recently discussed quite vividly at a Cardiovascular Cell Atlas workshop that was organized here at the Wellcome Trust. And Sarah Teichmann, Michela Noceda, Mike, and Sanjay have organized this. And I think it had a big response. There were also a few international people there. And it was really a day of full, vivid discussions. And I think our discussion today in the breakout session has recapitulated this largely because there was a large overlap of people that were here today and also there. Some of the initial cardiac work is also supported by the CZI, so we are very grateful for this, but this is not about that. It's just to actually demonstrate what the problem is. So we have extreme heterogeneity in the cardiac tissue with many different cell sizes, and basically ranging from very large cells to very small cells. That's one of the problematic features. The cardiac myocyte size is very large. It's up to 120 micrometers. So it's for many of the microfluidics that are available today, too large, and the shape is rather odd and problematic. And last not least, we have a big problem because the cardiomyocyte is often multinucleated. So even if we do single nuclei sequencing, we are not really aware of the consequences of multinucleation effects on that. However, we think we can circumvent these problems, and I will show you a bit on what we have discussed and what different facets we have discussed to tackle this and what's going on. But we also think it's important to study cardiac healthy tissue in different developmental stages and to create actually a developmental atlas. And I think the same, what has just discussed for the development also holds true for any tissue development, and we are aware this is a tricky part, but and also we need to take this to an adult cardiac atlas, and of course it has not only technical tasks that we need to overcome, I think it will lead into a new range of functional studies if we can overcome this initially in healthy tissue and then project this out to functional analysis and into disease. So what are the practical challenges that we have discussed for a developmental cardiac atlas? So the whole heart analysis of the earliest available stages is actually feasible. We can get access to tissue, however, of course, with the limitations to do this really in a very ordered and controlled fashion. And from a technical point of view, fetal tissue is much easier to handle than adult cardiac tissue. Of course, the acquisition of tissues is, for certain stages of development, easier than for others, and I guess we have touched upon this. And there is a need and sometimes also already established centralization of fetal tissue collections, and we would benefit from established logistics and ethics here. But I think these were similar things we've just discussed that were just summarized in the developmental breakout session. So what are the practical challenges for the adult cardiac, for an adult cardiac cell atlas? First of all, it's not an easy task to disaggregate cells and to bring them into single cell suspensions from cardiac tissues. The cell size I have mentioned. We have multinucleated cardiomyocytes, and we need to develop technical approaches that can address this, and this is underway, and I think we as a cardiac community are very optimistic that we can overcome these. But of course then there is the problem of acquiring, of course, healthy organs, and but there are also possibilities and ways around this. For example, there are people who die of brainstem death for many different reasons, and of course their cardiovascular system is by and large unaffected. However, this is also not true because there's a large hormonal response when you die, and that affects basically the entire physiology and pathophysiology of a human body, even if you die because of a motorcycle accident. So we can get apparently healthy tissue, but we have to keep in mind that this is not probably reflecting ultimately what is truly healthy. But I think there are also ways of perhaps comparing this in different ways and overcome some of these limitations. So what does at least some of us think that is important to study? The heart is not as a simple organ that may appear to be. It has 4 different chambers with different functions. It has many anatomical regions that have different functions. So we think we initially at least need to address this and need to analyze the 4 different chambers. We need to sample and analyze the interventricular septum that divides the left from the right heart. We need to look at the valves that are important for blood flow direction in the heart. There is an important anatomical region which is called the outflow tract, and last not least, there is a conduction system that actually makes the heart beating, and these are highly specialized cell types that we need to address. Of course, I think this is not specific to the heart anymore, how deep do we need to do this, and how many samples do we have to analyze to at least to begin to assess individual variability and variation. So let me just briefly run over, I think, what we felt are the most important points that we as a community have to address and that are underway in many different places already. I have mentioned the dissociation of cardiomyocytes and cardiac tissues, but cardiomyocytes are particularly difficult here to get single-cell suspensions in context of not disturbing the ratio between cells from heart tissue. We probably need to take up protocols of single-cell versus single-nuclear sequencing. I think it's synergistic, it's not versus, but we need to, at certain stages, resort to single-nuclear sequencing and complement this with single-cell sequencing, so there will be no one approach here. We will need to do this in multiple ways. We have to resolve whether multinucleation becomes an issue to perhaps bias certain results. We need to address sensitivity issues here. We need to control this by doing bulk sequencing in context of single-cell sequencing, and we need to take care that with all the dissociation protocols we still have, of course, high-quality RNA with any type of approach that we are using. So sensitivity issues are important. How far do we need to sequence to get rare cell types, especially, for example, in the conduction system, or do we need to take approaches to isolate this a priori? However, any type of manipulation will bring its own problems here to bear. We felt it's very important to assess reproducibility. Again, I guess that holds true for anything that we have discussed during the course of today and yesterday. I think an important issue here is as well the infrastructure. How do we go from the operating theater or catheter rooms to the bedside? That raises the importance of fixation methods. I think we have touched upon this too, so I think that is also not a particular specific issue for the cardiovascular system, but it is an important issue. I've mentioned the different anatomical regions, and of course we don't want to stop there, but the other technologies that we have discussed are of course also applicable within the cardiovascular system, but I think we wanted to give you a sense of priority that we need to resolve these ground issues before we can move into data acquisition and thinking of layering other information on top of this. Having said this, there's also, I think we have consensus that there's some good news. Rodent models, even though they are much smaller in size, the cell size of the heart is basically the same. So we can use and test a lot of these things in rodent models and ultimately apply these and to what I've just said for the human. Thank you.
Fantastic. Thank you very much. Questions, comments, thoughts from anyone in the room?
Really good job. Just the I've been thinking about the
elephant.
scale. Yeah, another elephant. Yeah, and actually, elephant size anatomic scale. So the sooner that we could have a common framework data model that's reusable over multiple systems, the better, so that people can really be, place their samples into a coordinate system so that it's referenced and we can start to stitch together the magnitude that when I look at from the base of the apex of the heart up to the where the valves are, and it just all of that's important as it thins out and then gets more and more valvular or perivalvular. It just so that all that detail of what's happening there and how events in the conduction system is kind of integrated over all of that. Everything we learned from the brain spatial coordinate really needs to be applied in organs in a consistent way. So I'm not sure I'm saying anything different than what you were saying, but I think it goes to this issue of should we have an anatomic scale coordinate data model sooner than later that all samples get annotated with that data model.
I can comment on that. I think the answer is yes, but also in recognition of the fact that anatomical scale model is not something you put ahead in advance and then everything is just pegged to it, that it's an iterative process actually. In humans, because they're actually variable in size and structure, and so having the thing defined in advance without any molecular and histological fiduciary information makes it sort of an impossibility. Whereas the ability to iterate back and forth as you go through it makes everything harnessed to each other in a truly meaningful way, and that's actually the outcome. That's the atlas itself. It's not something that precedes the atlas. It's part and parcel part of it. It's part and parcel. The atlas itself is not just about the cells, but it's the cells inside histological structure, inside anatomy at multiple length scales.
Just the more that we have kind of an a priori skeleton of the skeleton for those data tags, the better. And sure, it's not going to be an absolute coordinates. It's just there's a sense of where are you putting in, how are we even going to state those, coordinate scale features and sample.
Yeah. Michaela.
For other organs, are actually people taking measurements like the weight of the organ, the length, the depth, all of these measurements, and are they recording, I'm taking a biopsy 3 centimeters from the apex or whatever. So having those measurements that might sound gross for this audience where we are doing single cell transcriptomics, but I think they're the address of what we're taking those single cells, I think it should be, if it's not something to implement, which is very easily and rapidly done, but it would give at least a reference point.
I think, at least for the heart, we are in the very favorable position that, there are huge advances in MRI imaging. So we can do segmentations on heart basically it's fantastic resolution. And to actually integrate this also on an anatomical scale, of course, it's not at single cell, yeah? But you can actually, I think, relate ultimately where you have taken your biopsy from and make functional inferences also from other type of data like imaging data.
Okay, great. So we'll move on to the, thank you.